Today we have with us Pedro Mendes, who is a doctoral student in the CMU-Portugal dual degree PhD program, together with the Instituto Superior Técnico. His main research interests are around enhancing efficiency and trustworthiness of neural networks. And today's topic, enhancing uncertainty estimation in neural networks, is the result of his most recent research. Pedro Mendes, thank you for coming, and take it away. Okay. Yeah, thank you.
Hey everyone, thank you so much for the introductions. I'm Pedro Mendes, fifth year PhD student in the CMU-Portugal program. I'm a student at Técnico, where I'm being advised by Professor Paulo Romano, and at CMU, I'm being advised by Professor David Garland. And today I'm going to talk about my research on enhancing uncertainty estimation in neural networks. And in particularly, I'm going to first give a brief overview of my research in the past 5 years. And then I'm going to focus on the main topic that I'm going to address today, on the uncertainty estimation. I'm going to define the problem and then present the work that I have done so far, entitled Error-Driven Uncertainty Error Training. And I will finalize with the ongoing work that I'm doing right now. I plan to submit this work next week, and then I hope I can start to write the thesis and defend during the summer. So let's start. So we know that neural networks are used everywhere. We have a lot of examples. For example, for stock market prediction. When we Google something right now, we receive this summarization given, for example, by Google. When we use social networks, the recommendations that these applications gave, they also exploit this type of models. And even when we are using our smartphones, these models are exploited for diverse tasks. So when we are developing neural networks, we tend just to look for the quality, the predictive quality, for example, the accuracy of these models. But there are a lot of attributes that we should take care. And in particular, in this work, we focus on the efficiency and the trustworthiness of neural networks. And if I need to summarize my research in one sentence, I can say that I'm developing novel methods to enhance the efficiency and trustworthiness of neural models. And when I'm talking about efficiency, we focus on the problem of hyperparameter tuning. So when we are training the models, we need to perform this hyperparameter tuning phase that normally requires to train the model several times using different hyperparameter settings. And the hyperparameters that we use to train these models, they have a huge impact in the quality of the final model. So this is a fundamental stage when we are developing a model. Although this is very costly. As I told you, it requires to deploy the model several times using the different hyperparameter settings. And if we take into account the current architectures and models and the large data sets, the cost of the hyperparameter tuning phase is really, really impractical. So in the first half of my PhD, I was tackling exactly this problem to enhance the efficiency of neural models by introducing two methods called hyperjump and trim tuner that aim at maximizing the model accuracy while reducing the train and the optimization time via multi-fidelity techniques. And what is this multi-fidelity technique? So the basic idea is to reduce the amount of resources that we use to train these models. And this way we can get cheap and fast knowledge about some sets of the hyperparameter configurations. And then we use this cheap knowledge and extrapolate to the full budget. I will give you an example. So we select a bunch of hyperparameters to train the model. We train the model during 10 minutes, for example, on these sets of hyperparameters. We get and we collect this cheap knowledge, and then we extrapolate to the full budget. That can be, for example, training the model during 1 hour. And in these two works, HyperJump and DreamTuner, we exploit this type of techniques in order to reduce the training and the optimization time. On the second part of my PhD, we focus on improving the trustworthiness of neural models. And we can define trustworthiness using a multitude of different quality attributes. For example, reliability, security, explainability, fairness. In my work, we focus on these last two. So adversarial robustness and uncertainty estimation. On the adversarial robustness front, we perform a study where we evaluate the impact of performing hyperparameter tuning on adversarial trained models. So when we are developing adversarial trained models, the standard approach is to first, we train the model with clean data, just standard training, and then we have this pre-trained model, and we train it with adversarial examples to make the model robust against these attacks. So we have these two phases, the standard and the adversarial training phases, and they share hyperparameters, common hyperparameters. So our question was, should we borrow and use the same hyperparameters for these two phases, or should we perform a new optimization phase to select again the hyperparameters of the adversarial training phase? And the conclusions that we arrive is that we should perform first select the hyperparameters of the standard training, and then select on a new optimization phase the hyperparameters of the adversarial training phase. And this way we are able to improve the accuracy. Although this comes with a cost, because we need to perform the hyperparameter tuning phase twice, for the standard and for the adversarial training. So we also take this problem by borrowing some ideas from the multi-fidelity techniques that I just mentioned. So the thing that we were proposing was that, so let's use cheap adversarial training methods that are faster to generate adversarial examples, but also ensure less robustness guarantees. And let's use these fast and cheap methods to collect knowledge, and then use this knowledge to build models about the search space and extrapolate to the full budget, which in this case are adversarial methods that ensure higher guarantees in terms of robustness. And we implement this approach on a hyperparameter tuning optimizer, and the results that we got were very promising. We were able to reduce the cost significantly. And the last part of my research, we focus on improving the trustworthiness in terms of the uncertainty estimation. And this is going to be the main topic of my talk today. So we know that neural networks are often used in critical applications, for example, in healthcare areas or in autonomous cars. And it is crucial that these models can be trusted, so that we can understand and have some level of confidence in the predictions of these models. However, neural networks are overconfident. So even when they are predicting something wrong, they tend to be very, very, very certain that they are correct. And this is not a desirable behavior. So a key property when we are using and developing a neural network should be their ability to accurately assess their own uncertainty. And we have this notion of calibration, where the error should match the uncertainty. And the basic idea here is that if a model tells you that its prediction it has 80% of confidence, it means that for that level of confidence, it should be accurate 80% of the times. And this can be kind of translated in this graph, where in the x-axis, we have the confidence of the model. In the y-axis, we have the accuracy. And the blue bars represent the behavior of a neural network. So, for example, here in the area where we have low confidence, we see that we have higher accuracy compared to the areas where the model is is high confident. And this is not a desirable behavior. So perfect calibration is translating the red line and in these yellow bars. So in the regions where the model is not confident, it should be, the model should output lower accuracy, where in the regions where the model is accurate and is correct, it should be very confident about their predictions. So right now I'm going to talk a bit how can we measure the uncertainty of a neural network for a given input. There are a lot of methods in the literature. I'm just going to talk about this one, Monte Carlo dropout, because it's one of the most popular methods in the literature for uncertainty estimations in neural networks. And the goal and the idea here is to apply multiple dropout masks. So we activate and deactivate different neurons in the network. And for the same input, we perform several forward passes. So for a given input, we have a dropout mask, we perform a forward pass, we have a prediction. Then we change the mask, the dropout mask, we do a new forward pass, we have again a new prediction. So basically, we perform multiple forward passes with different dropout masks, and at the end, we are going to have multiple predictions for the same input. And we can aggregate these predictions by computing, for example, the uncertainty via the variance or the entropy. And this way we have an estimation of the uncertainty of the model. So next, there are several methods in the literature that they aim at enhancing the model calibration, and they can be divided in these two sets. So first, this first set, they implement a post-processing calibration phase. So the idea here is that we train the model, and then after this process, we perform a post-training calibration phase where we just tune the probabilities of the model in order to improve their uncertainty estimation. This orthogonal set of works, they account for uncertainty during training. So normally they encompass and they add a new term in the loss function that accounts for the uncertainty or for some measure of calibration. And these methods are able to improve the model uncertainty estimation during training by updating the model weights based on these loss functions. And the method that I'm going to present next, that was developed by us, it fits on this set of works. So our method, it's called error-driven uncertainty-aware training. It was present last year at ICAI, and the goal of this method is that we want to increase the uncertainty for misclassifications, and we also want to reduce the uncertainty for the correct predictions. And we want to keep the error of the model low. So we still minimize the error rate for both the correct and the incorrect predictions. And we achieve that by proposing a new loss function. And this loss basically employs two distinct functions, depending on whether the model is wrongly or correctly classifying a given input. So if the input is misclassified, we minimize the error and maximize the uncertainty. If a given input is correctly classified by the model, we want to minimize the error and the uncertainty, and this can be translated in these systems of equations where the red part is responsible to minimize the error and maximize the uncertainty, while the green part is responsible to minimize the error and the uncertainty for the correct predictions. It should be noted that this loss function is still differentiable and continuous, so we can apply standard and classical backpropagation based methods to compute the gradients. And so now let's look for a training epoch of this algorithm. So we need to first separate what is wrong from what is correct. So we need to query the model to determine the wrongly and the correct classify inputs. After that, we have these two sets. So the set of the mispredictions and the set of the correct predictions. And next, to reduce overfitting and also for efficiency reasons, we resize the sets. So both the sets of the mispredictions and the correct prediction sets, they have the same size. And then for a batch, we mix wrong and correct predictions. And this step is really important to reduce the overfitting. So after that, we have constructed our new data set, and we can use it to compute the loss function and run the backpropagation algorithm and update the model weights. And we perform this loop until some stop condition is met. So next, let's look for the experimental evaluation of our method. We evaluate EUAT on a set of different tests, on image recognition models, on binary classifications, on out of the distribution detection tests, and on adversarial training settings. We deploy our method and the baselines using popular model architectures and data sets in the image recognition domains, and we compare against 6 different baselines that aim to improve and to measure the uncertainty of the model. And overall, EUAT presents a better performance, and here I just want to highlight that EUAT has a superior performance in 16 out of 24 cases, and this is just for the image recognition models. If we account for all the task benchmarks models that we have in the paper, in the results, EUAT presents better results in 60% of the cases, and in the scenarios where the baselines present better performance than our method, these performance differences are very, very minimal, and this highlights the efficiency of our method to improve the uncertainty estimation. So now I'm going to focus on the ongoing work that I'm still developing. We are addressing the drawbacks that this previous method that I just present had. So EUAT was developed just for classification tasks. So basically, we need to separate from what is correct from what is wrong. And there are a lot of scenarios where this is not possible. And EUAT also introduced a significant overhead. In our experiments, on average, this overhead is 3.4 times. So we are addressing these challenges now. So let's focus first on the generalization of EUAT. As I told you, our method needs to separate from what is correct from what is wrong. And this is not always possible. For example, if we take into account summarization tasks or machine translation, we might have summarizations or translations that are better than others, but there is not this strictly hard division between what is correct from what is wrong. Also, regression problems. So in this case, the model outputs a number or a vector, and normally we measure the quality of the predictions based on an error metric, can be the distance. But again, there is not this hard division from what is correct from what is wrong, and even in the image recognition domain, the images they might have ambiguity. So in this example, is it a cat or is it a camel? So both animals, there are both animals in the image. The model should be able to classify the image as a cat with some probability as a cat and with some probability as a camel. And right now our method only allows use of true class, or it can be classified either as a cat or either as a camel. So we are addressing these problems now. And for that, as I told you, we have this step where we need to query the model to determine what is wrong from what is correct. And we want to remove this step and to consider a continuous characterization of the prediction errors. And if we go back to the loss function that I just presented in EUAT, our initial idea was to extend this. So we would still have a part in the loss function that is responsible to minimize the error and maximize the uncertainty. Another part to minimize the error and the uncertainty. And we would have these weights that would be calculated based on the loss value. And the idea here is that if the loss is high, it means that the model might be more incorrect, or the prediction is the probability of the prediction being correct is less. So we would give more emphasis to the first part, while if the loss value is small, it might mean that the model is correct. So we would give more emphasis to the second part in green, where we want to minimize the error and the uncertainty. Although this is not working. And why is that? So basically, we are just saying that the uncertainty should increase or should decrease. And we are not specifying by how much we want to increase or decrease the uncertainty. And when we evaluate this approach on different uncertainty metrics or calibration metrics, this approach does not work well. So we departed from this idea and we formalize our loss function as like this. So we want to minimize the error and some metric that we just call uncertainty error, which is a very vague name. And I'm going to tell you now how can we compute this uncertainty error. So our idea is that we want to compare the output and the desired distributions of uncertainty. And there are a couple of methods in the literature to compare distributions. For efficiency reasons, we want to avoid those. They normally have a overhead. So we avoid to use that, and we propose the following. So we want to measure the divergence between the predicted and the true distribution. So also, if we go back to the definition of calibration, the error should match the uncertainty. So our idea is to use the loss, the standard loss that normally measures the kind of the error as a proxy of the uncertainty. So the uncertainty should be proportional to the loss. And then we have this theorem that tells us that if the loss is strictly proper, if it's a strictly proper scoring rule, we can compute the divergence between the prediction of the model and the true distribution by computing the expected value of the loss minus the uncertainty of the true distribution. So the first term, the expected value, we can compute it very easily. The second part, in order to compute the uncertainty of the true distribution, we need to determine the true distribution. Although it's not that the true distribution is unknown and normally is not trackable, so we need to come up with a way to approximate that and to calculate it. And we resort in Monte Carlo dropout to sample that distribution. So basically, we perform several forward passes in the network to determine what is the true data distribution. So our new loss function, just to summarize, it's given by the error plus the uncertainty error, where the error loss can be computed, or the loss that we can use here can be a standard loss function, for example, the cross entropy, the mean square error, or the negative log likelihood. And to compute the uncertainty error, we propose to use the square divergence that I just present, and we use the square in order to this function to be differentiable. So the loss function that we are proposing to make our method general and improve the uncertainty estimation is given by the standard loss plus the square difference between the expected value of the loss minus the uncertainty of the true distribution. I start to collect the results maybe 2 weeks ago. This is still ongoing work. The preliminary results they show they are very promising. I will not show them here, but basically we are working on finalizing the results, and we plan to submit this next week if we can meet the deadline. So let's now focus on the other problem of EUAT, so the efficiency of this method. And first we need to analyze what are the sources of this overhead. And the first one is this step where we need to query the model to identify what is correct from what is wrong. But if we go back a few slides, when we address the problem of the generalization of our method, we said that we want to remove this step. So we already removed this step. So this overhead is solved. And the other source of overhead is the uncertainty estimation. So computing the Monte Carlo dropout. So as I told you, we need to perform several forward passes. And our idea here is that we can vary the number of forward passes to reduce the costs. We have some preliminary results here. So by increasing the number of forward passes, we see that the time increases linearly, and this makes sense because it's just a for loop. And then we evaluate this also on classification and regression tasks. And on classification tasks, we didn't see a significant impact in the quality of the uncertainty estimation by varying this parameter. But in regression tasks, we see and we verify a significant impact in the quality of the uncertainty estimation. And we are still analyzing this data, but the conclusion that we took here is that, so for regression tasks, what we are doing is that we have the model and the model prediction, and we approximate the model prediction using the Gaussian distribution. And to build this Gaussian distribution, we need more points, more predictions, while in the classification task, the output of the model is already a distribution. So you have the probability of each class. So you have more data points to build these distributions and to compute the uncertainty using, for example, the entropy. So just finalize my talk today. I start by presenting my research, and then I focus on this problem of improving the uncertainty estimation of neural networks. I present our method, error-driven uncertainty-aware training, that improves the uncertainty estimation by minimizing the error and the uncertainty for the correct predictions. and minimizing the error and maximizing the uncertainty for the mispredictions. As I told you, for the current research that I'm tackling, we are addressing the problems of the previous method by looking at the efficiency and generalization of EUAT. So this is the final part of my PhD. I hope I'm able to submit a paper next week, and then eventually I can focus on writing the thesis and defend over the summer. I want to thank you, Priberam and Gonçalo, for inviting me to be here today. Thank you all to be here and attend to my talk. And if you have any questions, please go ahead.
Thank you, Pedro. We now have some time for questions, and people on the Zoom can write in the chat. And, yeah.
Yes.
What is this distribution? So it is for that example that you are training on, or
you are talking about EUAT or the current work?
The current work.
Okay.
Yes.
And your question is?
The next one?
Yeah, P true?
Yeah, P true.
Okay. So the P hat is the distribution output by the model. So it's basically the model, the prediction of the model. P true is the true distribution, given that should be determined by the data that you have, although it's impossible and intractable to compute these. So normally what we do is that we can approximate this distribution using, for example, ensemble methods, or in this case, Monte Carlo dropout. So you perform multiple forward passes and you create this distribution, but it's an approximation. Yeah.
Sorry. Wouldn't it be okay for you to use some part of your training data to estimate that value before you do the training?
Yeah. So when you compute the uncertainty, we need to separate. And when we are talking about uncertainty, we need to separate between two types of uncertainty. The epistemic uncertainty that is due to the lack of knowledge of the model, or the aleatoric uncertainty, which is its source is due to the ambiguity and randomness in the data. In this case, we are not separating between aleatoric or epistemic uncertainty. The approach that you are suggesting of using the data to determine this would just focus on the aleatoric uncertainty, and the majority of methods in the literature, they do not want to do that. They want to focus more on the uncertainty of the model, which is normally determined via the epistemic uncertainty. Yeah. Yeah. Okay.
Entropy of V true is sort of an epistemic uncertainty.
Yes.
And you say that you're trying to force the model to be such that the entropy of the posterior distribution is close to the epistemic uncertainty.
Mm-hmm.
Why does that make sense? Why should the posterior probabilities should have an uncertainty which matches the epistemic uncertainty?
Okay.
You kind of sort of, if the epistemic uncertainty is high, you're trying to force the model to also have a high aleatoric.
Yes, yeah. So this comes a bit from how you define a correct uncertainty estimation. And there is this notion of calibration that tells that the official definition comes from and the area comes from the classification models. So if a model tells you there is 80% confidence, it should be correct 80% of the time. There are some works that extend this for the regression problems. And our idea was to so we want to have a method that is general. So we need to account that not all the models are able to output a probability. So at least the models that we consider, they can output a distribution, and we want to match the distribution output by the model by a true data distribution that tells you, like, for example, if you go back to the image, that image, you can have a distribution that it has all the classes, and it has 50% for being a cat and 50% for being a camel. So we argue that the distribution that is outputted by the model should be similar to that one. I understand your point that that term it calculates the epistemic uncertainty, and I agree with that. The main problem is that we don't have really a way to determine at least I don't know a lot of aleatoric uncertainty methods for compute the aleatoric uncertainty. What I have seen is that, so there are a few data sets, they have the human annotations, and so basically the data already have a distribution, but for that you need normally human annotations, and there are not a lot of data sets in the literature. That's the next step of using these data sets that they have the soft labels instead of having like just one true class. They have a that's the next step.
I would say that in that case that you're wrongly treating the problem as a classification problem, and it's not multi-label.
Yeah. Okay.
That
Yeah.
example has two correct labels. Not...
Yeah. I see. Yeah. Okay.
Sorry, maybe I'm not understanding correctly the difference, but usually we calculate like significance values with p-values and confidence intervals to gauge how good the model performance is.
Mm-hmm.
How does that fit in or compare to your approach, what you are presenting here today?
Yeah. So, for example, in regression tasks and regression problems, what people are doing is exactly what you are saying. So you have you normally approximate the output of a model given using a Gaussian distribution, and then you compute some confidence interval based on the variance. When we are using different models, for example, the classification models, we don't do that. So you just use other metrics, for example, the entropy instead of the variance to compute the uncertainty of that distribution.
But for example, in classification tasks, you can bootstrap the confidence interval, and that seems fine. No?
But you are suggesting in approximating the output distribution using some kind of distribution and then compute.
Yeah, it's bootstrapping the.
Yeah, so we avoid to do that because since we have the output of the model is already like the probability for each class, so you already have a few points. You can directly use those points to compute the entropy. I would say that your approach should be also valid, but it adds this assumption that you need to model the prediction of the model by some distribution.
Okay, thank you.
Any more questions?
So, especially, well, the first one, but maybe also this one. How does it work when you have really unbalanced data sets?
Really unbalanced data sets.
Fraud detection.
Yeah. So we didn't look into that. So I really don't have real data to answer to that question. That would be a nice problem to look, definitely. I would say that we could apply some techniques that are applied on when you have these problems for addressing the problem of the class imbalance, and they would still work here, but we don't have enough data. We didn't deploy those experiments. We have some experiments in out-of-distribution detection tests. So, for example, we trained the model using Cypher 10, and then there is this other data set. There is a Cypher 10 with corrupted images. And in these scenarios, our method still performs quite well. And we evaluate the model in a bunch of different metrics. The ones that normally we perform really well is this Wasserstein distance. That's basically, it aims at calculate how separate are the two distributions. And this is exactly our goal here. For example, if we look for the results of the latest approach that we are doing, that we are proposing, we see that on this metric, our new loss function is not so good as this previous one. But for example, in correlation with residuals, so the correlation between the error and the uncertainty, we are able to improve on that.
Okay, Pedro, thank you. Another round of applause to Pedro.
Thank you.
See you in 2 weeks for the next seminar.